The position of the ELR in relation to the other two lines, namely the DALR and the SALR, determines how we classify the stability of the atmosphere, as you might expect. Because we are considering both the DALR and SALR, the temperature and the humidity have a say in this classification. So, if the ELR is greater than the DALR, then the atmosphere is defined as being absolutely unstable. This situation is not common within the atmosphere and only happens just above the surface on sunny days. If a parcel of warm air is rising, it's warmer than its surroundings, the ELR. It will continue to rise, expanding and cooling as it goes until it reaches the same temperature as its surroundings. Now let's look at the opposite case. If we consider this part of the ELR, then the situation is defined as being absolutely stable. This is when the ELR, the environmental lapse rate, is less than the SALR. Therefore, the parcel of air will never be warmer than its surroundings, and so will stay in the same approximate position. The final scenario we must look at is in this part of the diagram. So the ELR is said to be conditionally unstable if the lapse rate is less than the DALR, but greater than the SALR. This is an important point about stability, which is sometimes not fully understood. The air is stable if dry, but unstable if saturated, and the situation is then called conditional instability, because the stability depends upon whether or not the parcel of air is saturated or unsaturated. There are two final scenarios we must look at which are linked. When the air is saturated and the ELR happens to fall on the SALR, then the atmosphere is said to have neutral stability. Similarly, if the air is unsaturated and the ELR happens to lie along the DALR, then the atmosphere is again said to have neutral stability. So far in this lesson, we have looked at how dry and saturated air behave when forced to rise within different environmental lapse rates. Using this graph, we saw that the value of the ELR and its position helped us decide the stability of the atmosphere. Now let's consider what weather you will encounter with the different types of stability. First, let's look at an unstable atmosphere situation. In this scenario, our parcel of air is warmer than its surroundings and can be described as buoyant. It will therefore naturally want to rise to a higher level, expanding and cooling as it does so. This situation is associated with convective type cloud, cumulus or cumulonimbus. This type of atmosphere is quite bumpy or turbulent, especially in the clouds themselves. With convective cloud, we get our vigorous updrafts within clouds which support large water droplets. This has two effects. It will therefore naturally want to rise to a higher level, expanding and cooling as it does so, but is usually rain, hail, or snow, or perhaps a mixture of all of these. It's very important to know that there's a significant increase in the icing risk within these convective clouds. We'll look at this in detail later, but note at this point that this is the IKO symbol for moderate icing, and this is the one for severe icing. The icing risk for aircraft in large cumulus cloud, whose temperature is low enough, is classed as moderate, occasionally severe. The icing risk associated with cumulonimbus clouds is always severe. One other thing to consider is the visibility. In an unstable situation, there is lots of overturning of the air, creating a great deal of mixing. This spreads any airborne pollutants through a great depth of the atmosphere. Therefore, the visibility is usually very good within an unstable air mass. The exception, of course, is when a heavy shower is occurring. Under precipitation, this visibility temporarily reduces, and in snow showers can be extremely poor, often as low as 500 meters. Now let's consider the weather when we have a stable atmosphere. Our parcel of air in this situation does not inherently want to rise when nudged upwards. If forced to rise, the parcel of air will cool more rapidly than the surroundings. This makes the parcel of air denser and heavier than its surroundings. Therefore, when the lifting force is removed, the parcel will want to return to its original position. The atmosphere is said to be stable when this condition exists. That is, it's very resistant to vertical uplift. The types of cloud we should immediately associate with this type of atmosphere are clouds of relatively little vertical but large horizontal extent, that is, stratiform cloud. Note that these sizes are relative. Stratiform clouds can be quite deep vertically, say 3,000 to 5,000 feet, but then usually have a horizontal extent of several kilometers or tens of kilometers. Due to the lack of great overturning within the atmosphere, there is usually little turbulence within a stable air mass. Due to the vertical motion of air, the precipitation associated with stable air masses tends to be of rain or drizzle, or perhaps snow if the temperature is low enough. It's characterized by its persistence and intensity, usually lasting for a longer period of time. That is, it's quite persistent with a slow onset and cessation, rather than sudden, which is often the case with showers. The precipitation is usually made up of smaller drops, as the moderately rising air cannot support water droplets of any great size, hence lighter rain, drizzle, or snow. Because of the absence of large supercooled water droplets, the icing risk is usually light. There are two big exceptions to this situation, however. The first one is when the temperature structure is just right to give freezing rain or drizzle. This is a serious hazard, and is also called ice rain or drizzle. We shall look at this in detail later, but in non-summer months, if the temperature is reasonably low, always spare a thought for freezing precipitation when flying ahead of a warm or occluded front. The other situation when the icing risk can be significantly increased is again ahead of a warm or an occluded frontal system, but this time over high ground. As the frontal system approaches the high ground, the lifting of the air is greatly enhanced, forcing a large number of water droplets higher into the atmosphere. This can make the icing risk moderate, occasionally severe, especially in nimbostratus cloud. With a stable atmosphere, there's little vertical movement of air. We find that airborne pollutants tend to stick in the layer where they are initially introduced. As the Earth's surface is the source of most pollutants, the visibility low down in the atmosphere is often moderate to poor in a stable air mass. This completes the lesson on adiabatic processes and stability, but both of these concepts will crop up again in other areas of aviation meteorology.